So we're continuing our journey to getting electron configurations. We want to be able to do the electron configuration of any atom or any ion that we're presented with. So our part 2 is looking at what's called sublevel splitting, sublevel splitting, and a rule called Hund's rule. So let's work our way through that. All right, so we know that in the second level, in the n equals 2, that there's 2 sublevels. So we learned this in the last chapter. When n equals 2, we know that L is equal to 0 or 1, okay? So we have 2 sublevels for every level, okay? This was our S sublevel, this is our P sublevel, and then this would have 0 for M sub L, -1, 0, and 1 for L. So we have our values for our orbitals when we're in the second shell. So there's 4 orbitals there in that second shell. Now when we're in the hydrogen atom, this S and this P sublevel have exactly the same energy. And we use the word degenerate, sorry, don't want to use that word yet. So they have the same energy when they're hydrogen, but as soon as you stick a second electron in there, the interactions of those electrons cause those energies to not be the same. It causes them to split, okay? If they have the same energy, we use the word degenerate, okay? I don't know why, they're degenerate orbitals, okay? And once I'm fumbling through my words, so let me get this. They have the same energy in hydrogen, but once you get more than 1 electron, they split, okay, and they no longer have the same energy. All right, so here is a picture representation of what I just said. On the left of the screen, we have, and we see up there, the word hydrogen underlined in red. This is what the orbital energies look like for a hydrogen atom. So notice down at the bottom we have the 1s. It has the lowest energy state. And when we go further out to the second shell, okay, we have the S and we have the P. These have exactly the same energy in the hydrogen atom. Here they have, when we go to the third shell, the S's, the P's, the D's, they have all the same energy. And that's why when we drew the hydrogen atom, we could say, you know, here's the energy of the 1, and then the 2, and then the 3, and they got closer and closer as they went further away, because we're looking at all the possible energies of all of those sublevels, and they're all the same in the hydrogen atom. And that's why the electrons, the spectrum of the hydrogen is very simple and very easy to translate. But over here on the right, we have the mini electron, anything more than 1. And when we get to the n equals 2, we notice that the S and the P don't have the same energy anymore. The P is higher than the S. And then when we get to the 3, we have the S, the P, the D, we have all of those. They're splitting in their energy. And then my 4s are splitting in their energy. So we have my 4S, my 4P, and my 4D. So that is a mini electron system. Now what we do know for certain is when that splitting occurs, the S's will always have the lower energy, and then the P's have a little bit more than that, and then the D's a little bit more than that, and then the F orbitals are going up from there. So that's the split that happens. When we start doing electron configurations, we have to know the order to put electrons in if we're going to do ground state electron configuration. So we have to know that order on the right. And when you look at that order on the right, it looks pretty complicated, because notice that when the S's split here, okay, when they're splitting in their energy, the D ends up being higher in energy than the 4s, okay? So it's even above the 4s. So when we get and start putting electrons in these areas here, into these orbitals, we would have to put electrons into the 4s before we could put them into the 3D. Okay, so the splitting that I talked about has a threefold cause. It's Coulomb's law, it is shielding, and it is penetration. I want you to be responsible for those 3 reasons. And you'll find that in your textbook. I will let you know where. But also in your textbook, there's something called a conceptual connection. It helps you understand that concept. So I want you to test your understanding of those 3 things with that conceptual connection. Okay, so let's move on. So we're going to now do electron configuration for more than 2 electrons. We did 1 and 2 and showed you the electron configuration, the orbital diagram, quantum numbers of the first 2 elements, hydrogen and helium, where we're only putting electrons into the 1s subshell in that orbital right there. So now we're going to go beyond that. All right, so we're going to be able to write the ground state electron configuration, making sure we put them in the lowest energy level and moving up from there. And this principle that we use to do this is called the Aufbau principle. Aufbau principle is a German word meaning building up. We're going to build up as if we're putting electrons in one at a time from the lowest energy up to the highest energy. Now for the atom, they don't, all stand around waiting for the first one to fill up. They just automatically go to these spots. But for us, when we write the electron configurations, we're always going to want to build up from the lowest energy and move our way from there. Now, when you look at this diagram here, and let's kind of focus in on it a little bit, it's very important that you know the energy of the orbitals. I'm going to show you eventually how to use your periodic table to come up with this. But for now, what we see here is if we write every sublevel that is in each shell. So here's the first shell. There's only a 1s sublevel. In the second shell, there's the 2s and the 2p. In the third shell, there's the 3s, the 3p, the 3d. In the fourth shell, there's the 4s, 4p, 4d, 4f. So we just write these down, and we'll never have to go beyond F. So while this does have a G, and this has an H, and this has an I, we'll never write those down because you'll never see anything more than an F. Once you write those down, then you can just draw diagonal lines through it, and those diagonal lines point you in the direction of the order that you fill. So you fill the 1s first, okay, and then you finish that arrow and you go to the next arrow, and then you're at the 2s. You finish that arrow and you come to the 2p. You finish that arrow, no, you're not finished yet, you're going to go to the 3s, okay, that's the end of that arrow. Then you come up here and you have the 3p and the 4s. 3p, 4s, and then you have 3d, and then you have 4p, and so forth. Okay, so this tells you the order they're filled according to that Aufbau principle as we go. I would never want you to memorize this order, but you can either construct it by reconstructing this little diagram and drawing your arrows through, okay, to know the order they filled. Or better yet, here in a little bit I'll show you how to use the periodic table. But that's the order that they're filled in, and you're going to refer to that for a little while as we go through and do these electron configurations. All right, so what I'm going to do on the board is I'm going to kind of construct this table, and we'll build this table together. So we've got our element, move it over as far as I can. My first element is hydrogen, and then we'll do helium, which really we've done the electron configuration for already. Then we've got lithium, and we have beryllium, and we have boron. So we're going to do those first elements first. So the first thing that we're going to do is the orbital diagram. Now rather than drawing boxes, I'm just going to draw lines, okay? So because boxes are just a pain. So there's my box, my 1s orbital, okay? It has 1 electron in it, so I draw it as an up arrow. The electron configuration I would write as 1s1, which we've already done, and for hydrogen our 4 quantum numbers for that electron would be N of 1, that's that number, L of 0, S is 0, the orbital 0, and it has a spin, and since I drew it pointing up, I'll do plus 1/2. So there's its 4 quantum numbers. Okay? Now we'll do helium next. Helium has 2 electrons. We know that by looking at the periodic table. It's element number 2. So we had the 1s orbital. We have its 2 electrons. They're spinning in opposite directions. We would do the electron configuration as 1s2. Now this doesn't give me quite as much information as this, but if you know anything about this and the Pauli exclusion principle, when you see that, you will know that they're spinning in opposite directions. So now there's 2 electrons, so there'd be 2 sets of quantum numbers because every electron has a quantum number. We've seen this before, but this is just a kind of a review of what we've done before. We have the one spinning in the plus 1/2 direction, and the other electron is in the exact same orbital, so the first 3 numbers are identical, and it's spinning in the opposite direction. So those are those electrons. Okay, so now we're ready to go to the next one. We have filled up this orbital, completely filled it up. So now we have to go to the next, and actually not only have we filled up this orbital, we've filled up this subshell, because that subshell, and we filled up that shell for that matter too. The N shell, the S subshell, the orbital, that's all that's there, and we now have to go further out from the nucleus. So when we go to lithium and we see that it's the third element on the periodic table, we have 3 electrons to work with. So we'll put the first 2 in the 1s, and then we have to say, okay, where does the next electron go? We look at our order and say, what is the next available sublevel in our energy going from low to high? And the next one is 2s. So that third electron will go right there. So when we do the electron configuration, we'll do 1s2, that's for those, and 2s1, that's that 1 electron in the 2s subshell. So this is the electron configuration, this is the orbital diagram. Now we already have the quantum numbers for those 2 electrons, but let's do the quantum number for this one right here. So this electron's quantum numbers would be, well, n is 2. It's the S subshell, that's an L of 0. There's only one choice for M sub L, that's 0. Remember, when L is 0, M sub L is only 0 because it goes from a negative L to a positive L. And I pointed this one up, so I will call it plus 1/2. Okay? Beryllium has 4 electrons, so we have 1s with its 2 electrons. We have 2s with its 2 electrons. Now we've got our 4 electrons accounted for. Electron configuration would be 1s2, 2s2. And if this first electron that I put into the s orbital was pointing up and the second one is pointing down, the second electron is going to have the same 4 quantum numbers. So this is the last electron I put in, but it's spinning in the opposite direction. Okay, so there it is, spinning in the opposite direction. So the first electron of these 2 right here, the first one looks like this, the second one looks like that. Now we're ready for boron. Boron has 5 electrons to deal with. Now let's see what we do here. We have the first 2, 1, 2, they're in the 1s. Then we go to the 2s, we fill it up, and I have 1 more to put in. When I put that 1 more in, it's got to go into the next available sublevel. We'll look at the order. What's next? Next is 2p. So 2p has 3 orbitals. So what I want to do is draw 3 boxes. 1, 2, 3. This is the 2p sublevel, and there are 3 orbitals in it. So I'm ready to put the next electron in. Now, these orbitals are degenerate. They have exactly the same energy. So I could put that electron in any one of those that I chose to put it in. It doesn't matter. It's all exactly the same energy. Now, I grew up here in the United States and I read from left to right, so I very typically put it here. Now, I can choose to put it up or I can choose to put it down. It doesn't matter. But because I'm an up kind of person and have an up personality, I make my first one point up. It's just what I always do. But you know, you might be Eeyore and you might want to point it down. I don't know. But that doesn't matter. You can put it in any one of these 3 and you can spin it in either direction. But since I put it there and it's spinning in the up direction, let's give the 4 quantum numbers for that electron. The 4 quantum numbers, well no, let's do the electron configuration first. It's 1s2, 2s2, and 2p1. Notice there's no splitting of those orbitals. When you do an electron configuration, you're just saying, I'm in the 2p subshell, and it has 1 electron, and it could go up to 6 because I can put 2 in each one of those. So that's as big as it could get, is a 6 there. So this doesn't show that there's multiple orbitals, but you know there are, because you know that in the p subshell there are 3 orbitals. Now let's do the quantum number for that electron, or this electron right here, okay? N is 2. L is defined by this value right here. When it's a p, that's an L of 1. Now, the next one I have 3 choices for. This one, maybe I'll call this one a -1, this one 0 and 1. That's not necessary. Those are the 3 I have. And going from smallest to biggest, that's how I'd label them. So since I put it here, I want to say that that's the -1 value. It doesn't matter which one of those numbers I chose to write right there, because it doesn't matter which one of these orbitals I put that electron in. but I chose to spin it up, so I'm choosing a plus 1/2 for that quantum number right there. So now we have the first 5 elements of our periodic table, and daggone it, I was going to ask you a question. I probably will. All right, so never mind. We'll come to that later. All right, so that's the one I was going to ask you, but I've already done that for you, so I will come up with a different question for you to answer. All right. We need another rule before we go to the next element, because when we go to the next element, we have to decide where the next electron is going to go. We'll get up to 6 electrons, and I have choices. The choice of putting it here or the choice of putting it here. I have actually 3 choices of where I could put that electron. Well, Hund's rule is what defines this. And Hund's rule says that the most stable electron arrangement is to put electrons in subshells that gives you the maximum number of parallel spins. So what does a parallel spin mean? A parallel spin means it's spinning in the same direction. So if I'm spinning this one up, I want to maximize the number of up spins that I can have, okay? So the result of Hund's rule is that you're going to half fill these orbitals so that I can parallel spin them. I cannot put a second orbital within the same direction here. That would violate Pauli exclusion principle. So I will spread them out and half fill before I go back and double up those electrons. Once I know that, then I can go on and continue doing electron configurations. So let's do carbon next. Carbon has 6 electrons. So the orbital diagram is 1s2. We put 2 electrons in the 1s. We put 2 electrons in the 2s. We draw the 3 orbitals in the 2p subshell, and we put the 5th one here, up spin, and the 6th one can either go here or here. It doesn't matter. Either one, as long as it's spinning, it has to spin in the same direction. Okay? Now when I do the electron configuration, I will write it as 1s2, 2s2, 2p2. And if you don't understand Hund's rule, when you see that, you might think they're in the same orbital, because these were in the same orbital, weren't they? But these are not in the same orbital. You have to remember when you're seeing that this is what it's representing. Electrons are spreading out and not in the same orbital. So if we did the electron configuration of these 2 electrons that I put in, these 2 right here, if we did the electron configuration, the first one is this guy. Okay, it is 2, 1, -1, plus 1/2. The next one, okay, that I'm putting in here, it's in the same shell, so it's still a 2. It's in the same subshell, so it's still a 1. But is it in the same orbital? No, it's in a different orbital here. So if it's in a different orbital, I have to make sure I use a different Sublevel. So I want to choose 0. Now what about the spin? Do I have a choice of spin? I don't. If I called this one plus 1/2, I know this has to spin in the same direction. So this one's plus 1/2, the other one has to be plus 1/2. So those 4 quantum numbers tell me about the second electron I put in. It's in a different orbital from the first one, but it's spinning in the same direction. So let's go to nitrogen next. Okay, for nitrogen, we have the 1s with its 2 electrons, the 2s with its 2 electrons. We go to the 2p, okay, and with the 2p, we do 1, 2, 3. How many have we done so far? 1, 2, 3, 4, 5, 6, 7. That's the electron orbital diagram of nitrogen with its 7 electrons. Okay, so what can we say about this last electron that we put in? If the first electron had this quantum number, okay, we see it there. The second electron had this set of quantum numbers. How about that third one? Okay, let's do that third one there. It's going to be 2, 1, because it's still in the second shell. It's in the p subshell, 2 and 1, but it's in a different orbital. The first orbital was a -1. The second one was 0. The third one is going to be a +1, but it has to spin in the same direction. Okay? Now I want Let's see, let's get started with the oxygen here, okay? Oxygen, 2 electrons, okay? 2s, 2 electrons, 2p. All right, now what are we going to do? We did 1, 2, 3, 4, 5, 6, 7. We need 1 more electron in. It can double up now, and it could double up wherever I wanted to put it. I like to put it there. Okay? So what I want you to do is I want you to answer the question that we see here. Which quantum numbers are going to be different for the last 2 electrons I placed in oxygen? So let me back up and place those last 2 in there again, okay? So I'm going to erase this if I can, without making too much of a mess. I did 1, 2, 3, 4, 5, 6. Okay, the last 2 would be this one. And well, 7, I'll do it kind of bold. 7, you're going to do that one. And then the last one I put in was 8, this one right here, okay? So those 2 that I kind of bolded up there, those are the last 2 that I put in. I want you to pick which one of those quantum numbers would have to be different for those last 2 electrons that I put in. Well, okay, hopefully you said that the M sub L are different because looky there, they're in different orbitals. The M sub L tells you which orbital it's in. And hopefully you told me that the spin would be different. That's the M sub S because one was pointing down and the last one was pointing up. Let me do the last one I put in. The last one I put in was right here, and it's in the second shell. It's in the P subshell. I went back to the same first orbital that I did when I did this one right here, so I called that one -1, and then now it's going to be spinning in that negative direction. So these 4 electrons that I have here are these 4 quantum numbers that we see right there, okay? They're all in the same shell. They're all in the same subshell. The first 3 are spread out with the same spin. The 4th one starts doubling up with the opposite spin. So there are those elements. Now I'm going to talk you through the next one because the next one we have here is fluorine and neon. What would we do? Well, for fluorine, the next one would go here, spinning down, right? And then for neon, the last one would be pointing down and filling up that P subshell. So when we finally get to neon, we have completely filled up the S and the P orbitals, or the S and P subshells, and we have completely filled up that second shell because once we've filled up the 2P, the second shell is full and we have to start moving out to the next subshell. All right, what I'm going to teach you next is how not to have to use that diagonal relationship that we talked about where we're going through and deciding what orbitals are we going to fill next, but how to utilize a periodic table and do electron configurations for any atom that you see on the periodic table. We'll learn kind of a shorthand method so we don't have to, if we've got something with 50 electrons, we don't have to start at number 1 and move our way all the way through. We can kind of start somewhere in the middle, and I'll teach you how to do that in our next lesson.